Thank you, David, for such a nice introduction. My name is ISHTIAQ AHMED and I will explain cases of interference test. Let us consider an active well at this point. Active well is either a producing well or injecting well, and the observation well is at the distance r from the active well. If we want to calculate stabilized well pressure, which is denoted by PWS, and it is equal to pressure at 1 hour plus m slope into log time t. We can use this relation only if the combination of 0.002637 permeability times T over porosity into viscosity into total compressibility into R square, the value of this combination is greater than 100, then we are able to use this relation. To calculate this relation, we have to first draw the graph between semi-log graph between PWS and time by using the given data. Then we will obtain the graph like this, and from this graph we are able to determine m of the straight line region. Once we get m from the straight line, the next step is to calculate permeability by using this relation. Permeability K is equal to 162.6 into flow rate viscosity into B over m into thickness of the well. By using this equation we can find the permeability of the well, and then we can, by using this permeability, we can find porosity. As we need permeability in this equation, which is porosity is equal to permeability over viscosity Ct R square exponential Pi initial pressure minus pressure at after 1 hour divided by m, which we have gotten from the graph, minus 3.2275, and then we have all the parameters required to put in this equation. As we have find permeability and porosity, then we just simply plug these values into this relation. The other all parameters are given in the data, and if the value is greater than 100, then we can apply this formula to calculate the PWS, which is equal to pressure at after 1 hour. This pressure after 1 hour we simply get from the straight line as we have just drawn in semi-log graph into m, also from the graph into log t. This is how we find stabilized well pressure at observation well after time t. Now I will pass to my friend. He will explain the case 2. Thank you.
Hi everyone, I will continue after my colleague by explaining the second case in interfering test, which is active well is shut in after producing time TP. So in this kind of case, first we can calculate the well power pressure during shut-in by the following formula: PWS equal Pi plus m times the log of TP plus delta T over delta T. Notice that Pi is the initial pressure. Also, in this case we can calculate porosity and permeability, but to do that, first we need to calculate m, which is the slope. How we do that, you say? We need to first plot PWS versus TB plus delta T over delta T. After you plot, you will have a straight line in semi-log graph paper, which will directly give you the slope m. Using that slope, or after getting the slope, permeability can be calculated using the following formula: K equal to 162.6 flow rate times viscosity times formation volume factor over the slope m times the thickness. Second, porosity also can be calculated by the following formula: phi equal to permeability over viscosity times total compressibility times the area square exploration of P at 1 hour minus PWH at time equal to 0 over m minus the log of 1 plus 1 over TP minus 3.2275, all under exponential. Note that P at 1 hour is obtained from the semi-log straight line at delta T equal to 1 hour. Thank you very much, and now I will pass the audience to my next colleague. Thank you.
Hi guys, I'm Mark and I'll be talking about how we can use type curves in analyzing interference testing. This is a common question in exams, by the way. First off, we tabulate delta T and delta P as we intend to plot them against each other in the next step. Delta P are generally, of course, available, but we may need to compute the corresponding delta P values via the following equation. Pi minus PWF, Pi being initial pressure and PWF being bottom hole flowing pressure. PWF will be given for each time step if this is the case. Once we have that, we can begin plotting our delta P versus delta P on a log-log scale. We will be using a master curve for this. We intend to match to this curve with our own data later, and we will see how we do that in the next step. When plotting the points, we trace over the master curve to ensure that we have the same grid dimensions, and after plotting the points, we adjust the position of the matched plot to the master curve. We try to match the curves, and when we do this, the tracing paper can move horizontally or vertically, but it cannot at any point tilt to in any degree to the left or the right. Once we have a match, we choose a convenient match point, and we can proceed with the next step. When we read our match point, we pick a convenient point, and then we read off both axes, both the master curve and the traced graphs, and our match point selection should give us two sets of corresponding values: dimensionless pressure and delta P, and also TD over RD square and delta T. Ultimately, we can use these to compute both the permeability in the test region and also the porosity via the following relationships. This is where we put in our dimensionless pressure and delta P to compute for permeability, and then over here is where we use our delta T over TD over R square D, and this will give us our porosity. Okay guys, thank you. That was a brief overview of how we use type curves in interference testing analysis, and I'll pass it over to my colleague and he'll go through a couple of examples for you so you know how to do this in your exams. Thank you.
Well, hello everyone, I'm Mohammed FARIHIN, and I'm going to explain about procedures to calculating permeability and porosity using type curve. Basically, there are 4 steps involved to calculate the permeability and porosity using this type curve. And the first step will be by plotting the delta P versus T on the log-log graph. Remember, the value and unit must follow the field unit. For the second step is to matching field data to master curve. When matching the curve, make sure the scale and the size of the curve need to be aligned perfectly with the master curve to ensure best result. For the third step is to picking match point from both graphs. To make it easier, pick the intersection point on the plotted graph first, and from there choose the respective matching point from the master curve. Then jot down all the values of each matching point. So this is how the master curve will look like. After you get all the values, you continue with step 4, which is to calculate the permeability and porosity using the following formula. So this is the formula for permeability, and this is the formula for porosity. When you finish with the calculation, you might get a different values of porosity and permeability compared to your friends. This is because when you're picking up the matching point, everyone pick a different value. However, if this happens, I suppose that the acceptable difference is about 5 to 10% from the real answer. Now that we have gone through all the 4 steps, let's take a look at the example. Here is the example given. As we can see here, in the interference test data, the time and pressure given start at 0. we can ignore this value since we are going to plot our graph in a log-log scale, and log 0 is undefined. We can also see here in the test data, the last point in the given pressure data is stated as n. We can also ignore this point along with t equal to 48 hours because we can plot this data. So from all the 6 points given, you only need to plot only 4 of them. Okay, now let's solve the example step by step. For step 1, plotting the graph on log-log graph. This is a plotted graph you obtain from the data. For step 2, matching the plot with the master curve. As I have said earlier, we need to adjust the plot with the master curve. Here is the adjusted plot. Now that we have aligned the graph accordingly, we can proceed to step 3, picking the matching points from both graphs. Here in these examples, I pick the intersection point from the graph that I plotted which fall on the yellow circle. As we can see from the mesh, we obtain the following values. The values might not exactly be the same as from the original mesh, but it is acceptable. So from the matching point, we get the delta P equal to 100 psi, T equal to 10 hours, PD equal to 0.92, and PD over RD squared equal to 0.85. We take this point and proceed to step 4, which is calculating air porosity and permeability. Using the given permeability formula, you only need to put in every values inside and you will get the value of permeability equal to 4.991 mil-Darcy. Use this value to calculate the porosity using the following formula. Just put in all the values inside the formula and we get the value of porosity. The value of porosity we obtain from the calculation is equal to 0.085, which is also equal to 8.5% porosity. So basically, I have solved the example by following all the steps given. That's all from our group. Thank you for watching.